Number 7, we can do trig functions with implicit differentiation. There really is no limit to these. So sine is our outside function. So we're going to take derivative of it first. That'd be cosine of x times y. And now we're going to multiply this by the derivative of x, y. Again, that's that chain rule piece, not chain rule, product rule piece that we talked about earlier, that if you just know, we don't have to keep writing that over and over. So let's go back up to where we used it. We used it way up here, y plus x dy dx. I'll show you again where it comes from, but it would not be a bad idea just to know that. That way we don't have to keep doing it over and over and over. All right, derivative of x is just 1 dx dx. G would be y, plus f would be x, and derivative of y would be dy dx. And that's equal to 1. Derivative of x is just 1. Now, in this case, they don't want me plugging in a point. They want me actually finding dy dx. So we're going to have to go through and actually solve for dy dx in this case and get that by itself. So what would that look like? We end up with cosine xy. We can divide by all of that because it's being multiplied by all the other stuff. So cosine xy on both sides. So we end up with y plus x dy dx. 1 over cosine is equivalent to secant of xy. Then we can subtract y from both sides. So we get x dy dx is equal to secant xy minus y. And then we can divide everything by x to get dy dx by itself. So we get dy dx is equal to secant of xy minus y all over x. Done with number 7. Number 8, dy dx for tangent x plus y equals x. Derivative of tangent is secant. So derivative of tangent xy is going to be secant squared x plus y. Derivative of tangent is secant squared x plus y. Then we're going to multiply by the derivative of x plus y. Derivative of x is just 1 dx dx. Derivative of y is just dy dx. That's equal to x. We can divide both sides by secant squared to get dy dx by itself. Secant squared x plus y. So what do we end up with? We end up with 1 plus dy dx. I lied to you guys. Derivative of x is not x. Derivative of x is 1 dy dx. So 1 plus dy dx is equal to 1 over secant squared, which would be cosine squared x plus y. And then we can subtract 1 from both sides. So we get our derivative implicitly is equal to cosine squared of x plus y minus 1. Remember, derivative just refers back to this idea of slope of the tangent line. And this is a formula for the slope at any point. We could also find second derivatives, d squared y dx squared. This is the same idea as like f double prime of x, but since we're doing it implicitly, we're going to use the d squared y dx squared notation. So we're just going to find the derivative once and then solve for dy dx, and then find that derivative a second time. So derivative of x squared is 2x. Derivative of y squared is 2y dy dx. And that equals derivative of 100, which is 0. We can subtract 2x from both sides. So we get 2y dy dx is equal to negative 2x. We divide both sides by 2. Actually, 2y. Let's divide both sides by 2y. It cancels over here. So we get dy dx is equal to, the 2's cancel, negative x over y. And then we're going to take that derivative again. To take this derivative again, we're going to have to use quotient rule. Quotient rule, low d high minus high d low, all over low squared. So d squared y dx squared is equal to derivative of, we're going to do y first. Derivative of negative x is just negative 1 minus, we're going to do negative x first, and derivative of y is dy dx, or 1 dy dx. all over y squared. Clean that up a little bit. We get negative y. Negative times negative x would be positive x, dy dx, all over y squared. Technically, that would be our final answer, but there's that dy dx piece, and that can't, at the moment, stand alone, because we would need to know what dy dx is. But we do know what dy dx is. We know that dy dx, we found that earlier, dy dx was negative x over y. So we can just use that substitution right there, direct substitution there for that, all over y squared. We can make this look a little bit nicer. We got fractions inside fractions. We don't really want that. So we can multiply the numerator and the denominator by y to cancel that out. Y times y is negative y squared. Y times this x times negative x is negative x squared. And if we multiply the y by that, the y and the y are going to cancel. So the numerator, we get negative y squared minus x squared. Denominator, we get y squared times y squared, which is y to the third power. Now, we could keep going here. We could factor out a negative 1. We factor out the negative 1, we get y squared plus x squared, all over y to the third. And we know y squared plus x squared, or x squared plus y squared, is equal to 100. So this is actually equal to negative 100 over y to the third, because we knew what x squared plus y squared was based on the original problem in that case. On number 10, we're looking for the second derivative here using implicit differentiation. Derivative of y squared is 2y. So I get 2y dy dx is equal to the derivative of 9x, which is just 9 dx dx. We don't have to write that. Solve for y. We would just divide both sides by 2y. So we get dy dx is equal to 9 over 2y. We're going to find the second derivative here. We can use quotient rule, it looks like. Would be a good idea. So d squared y dx squared. We're looking at low d high minus high d low all over low squared. All right, the low would be 2y times derivative of 9 would be 0 minus 9 times derivative of 2y would be 2 dy dx all over 2y squared, which would be 4y squared. If we took quantity of 2y, squared it, that would be 4y squared. Clean this up a little bit. We get 2y times 0 is just 0. Negative 9 times 2 is negative 18 times dy dx, but we know what dy dx equals. We know that dy dx is equal to 9 over 2y. So we're just going to do that substitution here. 9 over 2y all over 4y squared. Negative 18 divided by 9 over 2y. We want to get rid of the 2y in the denominator, so we would multiply everything by 2y on the top and bottom. This 2y would cancel out. Yeah, that 2y would cancel out. And then we can do the negative 18 over 4 first. That's going to make our multiplication a little bit easier. Negative 18 is divisible by 2, and 4 is divisible by 2. So we end up with negative 9 times 9 is negative 81 on top. And 2 times 2y times y squared would be 4y to the third power would be our final answer for the second derivative, negative 81 over 4y to the third. All right, find equation of the tangent line. We can still do that using implicit differentiation. It doesn't really go away. This is x to the 1/2 plus y to the 1/2 minus 1 equals y. So we end up with 1 over 2 square root of x. And here's where that came from. We get 1/2 x. We're going to subtract 1. We get negative 1/2. So we can go ahead and move that to the bottom, make it positive. We can do the same thing with y to the 1/2. It's going to be 1 over 2 square root of y. So that's got to be our dy dx. Minus 1. Nope, not minus 1. The derivative of 1 is 0, so that piece just goes away. And the derivative of y is dy dx. We can go ahead and plug in our numbers, 9 and 4 at this point. So when we plug in 9 and 4, we can simplify that. We get 1 over 2 times the square root of 9 plus 1 over 2 times the square root of 4 dy dx is equal to dy dx. That's 1 over 2 times 3. Square root of 9 is 3, so that's 1/6 plus 1/4 dy dx is equal to dy dx. We can subtract the 1/4 dy dx from both sides. Just trying to get dy dx by itself. So everything that has a dy dx goes on one side. So we get 1/6 is equal to negative 1/4 dy dx. And then we can divide by negative 1/4. Or likewise, we can multiply by the reciprocal, which would be negative 4 over 1. Negative 4 and the 1s cancel. We get negative 4 over 1 over here. We get negative 4 over 6, which is negative 2/3 is equal to dy dx. So what is this? This is the slope of our tangent line at the point 9, 4. No, it's not. Okay, several ways to solve this. One way is to just get all the dy dx's on one side and combine them because they are like terms. So we end up with 1/6 is equal to, this is really 1 minus, these cancel out, and 1 minus 1/4 would be 3/4. If you had a whole and you took a fourth away, you had 3/4 left over. We would multiply both sides by the reciprocal of that. It cancels out over here on this side. The 4 and the 3 cancel out. So we're left with 4 over 18, which we can simplify into 2 over 9. And that's equal to dy over dx. So that would be the slope of our tangent line. We can plug that in. We already know our x values, x1, y1, and we just found the slope to be 2 over 9. So y minus y1 is 4. So we get y minus 4 is equal to 2 over 9 times x minus 9. And this 4 looks like a 9. So let's actually make it look like a 4. 4. And we can leave it like that. Right, we could go through and we could solve the problem. We could get y by itself, but that's okay for now. Number 12, we would do likewise. We're going to have chain rule on the left. We're going to have product rule on the right. But the idea there is the same. Number 13, we want to find the horizontal vertical tangents. Horizontal tangents are where the slope is equal to 0 or the derivative is equal to 0. So we're going to set dy dx equal to 0. Turns out that's just going to be the numerator equal to 0. The vertical tangents, we're going to set the denominator equals 0 because we want to know where the function, the derivative is undefined, and the derivative is undefined when the denominator is equal to 0. All right, we're going to take the derivative of this implicitly. The derivative of 25x squared is 50x squared dx dx. The derivative of 16y squared is 32y dy dx. The derivative of 200x is 200 dx dx. We don't have to write that. The derivative of 160y is 160 dy dx. Derivative of 400 and 0 are both 0. So that equals 0. Anything that doesn't have an x or dy dx, we're going to move to the other side. So we're going to subtract 50x squared and negative 200 from both sides. So we get 32y dy dx minus 160y dy dx is equal to negative 50x minus 200. On the left side, we can factor out a dy dx. We can't combine those or anything, so this is a nice little algebraic tool to help us take two things that can't be combined and actually turn it into 1. So we get 32y minus 160. I said 160y, but it's really just 160. And that's equal to negative 50x minus 200. And now we can divide by this 32y minus 160 on both sides. So we end up with dy dx is equivalent to negative 50x minus 200 over 32y minus 160. Now to find those horizontal tangents, we're going to set the numerator equal to 0. We get negative 50x minus 200 is equal to 0. Add 200 to both sides, we get negative 50x equals positive 200. Divide both sides by negative 50, and we get x equals negative 4. Now, the question wants the points. To save you some time, to save me some time to find those points, we would plug negative 4 back into the original equation up here into these spots where x is and where x is, and then we would go through and solve that equation for y. I'm going to tell you that you do get y equals 0 and y equals 10, but I'm going to save you some time by not actually working those out. If you do need to see those worked out, let me know. And then we're going to set the denominator, 32y minus 160 equal to 0. We're going to add 160 to both sides, and we get 32y is equal to 160. Then we take 160 and divide by 32 on both sides. And we get x equals, not x, but y is equal to 5. And then to solve for that, to figure out what the points were, to figure out what the x values were, up here where y is, you would plug in 5, and then you solve that equation for x. It actually ends up being a pretty simple equation. You end up with 25 x squared plus 200x because all the constants cancel out. And once you solve that, we end up with x equals 0 and x equals negative 8. So that would be our 2 points. We need x and y values if they ask for points. That's all of chapter 11. This is taken from Master Math Mentor. Here's the website for that, the basic website. He's got lots of great resources out there for AP Calculus AB, AP Calculus BC, as well as a bunch of other courses such as AP Statistics and Pre-Calculus. If you have any questions, you can reach out to me on Remind, and I'll be happy to answer those for you. It may take me a minute to reply, but I will get back to you as soon as I can. Hope you have a good day.